want to start just by finishing off one, or rather pointing out one consequence of what we did yesterday. So we saw yesterday that if X is a normed vector space, and its dimension is finite, then any linear map, or all linear maps, from X to any other normed vector space are continuous. And that's the same as being bounded in the sense that we talked about last time. So an important consequence of this is that if you have X equipped with two norms, so I'll call them norm A and norm B, then you get two different normed spaces, one with the vector space X with this norm, and the other the vector space X with this norm. And the identity map so the linear map that's just the identity on vectors, you can think of as a map from this normed space to this normed space, and it and its inverse, which is also just the identity, are automatically continuous when X is finite dimensional. Okay, so as is its inverse, and that means equivalently that they're bounded. And so just to cash out what that means, it means that the image of a vector, so the norm, sorry, make that a lowercase, the B norm of the vector X is bounded by a constant times the A norm of the vector X. And that's using continuity of the identity map going this way. If you use the continuity of the identity map going this way, you get a sort of complementary inequality. You get, say, maybe I'll call that C1. So the A norm of X is then bounded by some constant times the B norm of X. And whenever you have both of these things, a norm bounded by a constant times another norm, and vice versa, this norm bounded by a constant times that norm, we say the norms are equivalent. Okay, so in finite dimensions, all norms on a finite dimensional vector space are equivalent. You had in metric spaces, you had examples, if you look at infinite dimensional vector spaces, like, say, sequence spaces that are square summable and absolutely convergent, then those two notions of convergence or continuity or just the norms are not equivalent. So in infinite dimensions, this is no longer true. Okay, so one of the convenient things about finite dimensions is that whatever norm we use, every other norm that you might use is equivalent to it in this explicit sense. So the one norm, the two norm, and the max norm that you used regularly in the metric spaces course, all those three norms are equivalent, and you could show that directly. But this is saying that whatever norms you put on Rn, it's equivalent to, say, the Euclidean norm. Okay, and that you can think of as saying, well, okay, I don't need to care. Let's just always use the Euclidean norm. In reality, it's useful to know that every norm is equivalent to the Euclidean norm, and sometimes it's more convenient to use a different norm, like when we proved this statement that any linear map is continuous if its domain is finite dimensional, it was easiest to start using Rn with the one norm. Okay, so the main topic for today is what is differentiability. Okay, so what we want to do is want to have a sensible definition for, say, a function f defined on some subset of a normed vector space. So let's say U is an open subset. And X is a normed vector space in which U sits, and F is just some map from U to Y, where Y is another normed vector space. So remember that imposing the condition that the vector spaces have norms is just a condition that means it will make sense to talk about limits and to talk about continuity. So the derivative is going to be defined in terms of some kind of limit. So we need a norm, we most likely need a norm for that to make sense. But I want to know what it means for f to be differentiable. Let's see, definition for f where to be differentiable at some point in its domain. And we'll take the domain to be open just so that at any point we know the function is defined sort of in every direction nearby. So that's just a convenience for this setup. Now, the one variable definition well, what did that say? That said, suppose f's a function on, let's say, an open interval, taking values in the reals. Well, then we can say if c is some point in the interval, f is differentiable at c and has derivative f prime of c if this limit exists. Okay, and when you move to thinking about maybe functions from the complex plane to itself, this definition is fine, right? Because you can just literally transpose it word for word. Take this to be a complex number. You can divide it by h because you can divide complex numbers. So for metric spaces in complex analysis, it was fine to take this definition and sort of read it to say complex numbers rather than real numbers. But if f is going from an open subset of a normed vector space X and landing in a normed vector space Y, this definition is not helpful. Right, I mean, there's a number of problems. I'm dividing by h. So if h is a vector, then I don't know in general what it means to divide by a vector. It's probably too much to hope that I can make sense of that for an arbitrary vector space. And then even if I did, it doesn't really solve the problem that you have because the numerator and the denominator live in different vector spaces. So dividing one by the other, even if I knew how to divide by vectors, wouldn't really help me because I'd need to figure out how to divide by a vector in a different vector space. So this definition is sort of set up in a way that is really designed to obscure how you might generalize it to vector spaces. But let's think for a moment, can we learn anything if we assume that x and y are one-dimensional? Right, so that seems like it is just this situation. The only difference is I'm sort of abstracting it a little bit, so I just have some one-dimensional vector space with a norm and some other one-dimensional vector space with a norm. But that's not really an issue, right? I just need to take coordinates. And I can reduce both of those to something which is just a copy of R. So one solution would be to say, well, okay, in the one-dimensional case, surely we're fine. We just pick coordinates, write down the function from the reals to the reals associated to picking coordinates, and then take the derivative of that function. Now, so let's do that just to see what happens. So let's say pick x0, a non-zero vector in x, and y0, a non-zero vector in y. So those give you a basis of x and y respectively. And I can write f of, let's say, t times x0. So this is an arbitrary vector in here. Let's call that capital F of t times y0, right? Any vector in capital Y is just a scalar multiple of y0. So this thing has to be just a scalar times y0. So I get, just by picking coordinates, this function capital F is just a real valued function on the real line. So let's say, for example, at 0, we can ask if the derivative of capital F exists, and that's just from the definition up there. So does i.e. Okay, and if it does, then we could go, well, maybe that's what we want to call the derivative. The only issue is that we have chosen coordinates, so if we want an answer that really is just intrinsic to the norm vector space, we should check that it doesn't matter what coordinates we pick, right? So if we take, let's say, x1, and y1 some other choice of vectors, which are non-zero, then x1 is going to be some multiple of x0, and y1 is similarly going to be some multiple of y0. And then we'll get a new function f, maybe I'll call this one f0, and the new function f1. So the way I've defined it up here, I would have f of tx1 should be capital F1 of t times y1. Now let's just translate what that means in terms of x0. So t times x1 is f of t, or lambda t, x0, is therefore f1 of what I'm calling t, and y1 is mu y0. Okay, and then this is just f of lambda of t times y0. Right, just take the definition up there, using lambda t instead of t, that gives you this. And so you see that f0 and f1 are related by, a reasonable transformation, but it's not the identity. So f1 of t is mu inverse f0 of lambda of t. And so what that means is that the derivative, when I chose the coordinates x0 and y0, that will get multiplied by, in the corresponding thing if I use the derivative of the function f1. They're related by, well, just this expression here, right? That f1 prime at 0 will be lambda mu inverse f0 prime at 0. Okay, so it does depend on the coordinates. Okay, so what this is actually just telling you is that the derivative is not a scalar. Right? It's not whatever it is, if it's going to map between x and y, it's not a scalar, but you already knew that because if you did physics or ever had anyone make a sort of intuitive explanation of the derivative, it's supposed to be rate of change. Right? So for example, velocity has units, right? It's meters per second or whatever your choice of units is. And this is just reflecting exactly the same thing. So this just shows that the derivative is not a scalar. Right? It transforms. I mean, it is something we can calculate in coordinates like this because we know how to relate the thing we get when we change coordinates. So in that sense, it's no worse than a scalar, but the thing to realize what it's actually doing is that the derivative is actually a linear map. Right? The scalar that you get from the ratio is just giving you a 1-by-1 matrix, if you like. So the derivative of this function f mapping from x to y, when x and y are one-dimensional, should be thought of sorry, I should say at 0. As the linear map. Let's write it like this, f prime to 0, which sends x0 to this scalar times y0. So it may be given by. Okay, and if you think, and viewing it this way, this calculation that we did, the calculation of how it behaves when you change coordinates, is just the 1-by-1 case of, if you like, A goes to PA Q inverse. If you change bases from, if you have a linear map from a vector space X to a vector space Y, you write down its matrix with respect to some basis in X and some basis in Y. Then when you change the basis, you have to change, the matrix gets altered by the change of basis matrices on the source and the target. And that's just exactly what we saw in the 1-by-1 case. Okay, so if you like, that tells us what you should do with the fraction. So thus, we should view this expression that you get taught as the ratio defining the derivative one thing you can always do whenever you have an expression which has a fraction in it is you can just clear denominators and say, well, this divided by this equals f0 is the same as requiring the limit as h goes to 0 of 1 over h f of h minus f of 0 minus f primed of 0 applied to h. I'm still dividing by h here, but we can replace that by dividing, say, by the length of h. Or indeed, what we can do in the one variable case, or mimicking the one dimensional case, is just take, so yes, let's see. This expression has the advantage that it sort of tells you, if you just look at that, it's a product in the real variable case. But if you're thinking f is going from one vector space to another, then it's sort of obvious that this thing has to become a map from x to y so that you can compare the vectors f of h and f of 0, which lie in y. This thing is going to have to lie in y also, which tells you that this thing should be some kind of function from x to y. And then we want this difference to go to 0 after we scale it by something which should be related to this vector h. Okay, so from this we get sort of, I guess, proposal 1. Oops. For what we might define the derivative to be, right? So we could say we want a linear map because that's what we got in one variable case. And what properties should it have? Well, it should have something like this tending to 0. Sorry. So what we can do is say that if we have a vector in x, then the derivative at 0 on that vector should be the limit of f of 0 plus, if I just use a scalar t to vary the length of the vector but keep it in the same direction, then I can consider the difference of f of 0 plus sort of a small perturbation in the direction v minus f of 0 all over t. And then here I'm just dividing by a scalar, so this is one way to escape from the division by vector problem, and then just take the limit as t goes to 0. Okay, so this thing gets called a directional derivative. So it's the directional derivative at 0. That's the point you're basing your measurements of the function f from in the direction v. And we'll probably denote that as a kind of partial v of f at 0. Okay, so this is one sort of reasonable candidate. I guess if you have f taking values in a vector space, you know how to multiply and divide by scalars. So you can use the direction of v to move, consider the change of the function f as you move in the direction v infinitesimally, in the sense of move just a very small amount in the direction v, subtract the vector that you were originally, divide by t, and see if that tends to a limit. So that gives you, where it exists, a well-defined function. So thus, this proposal gives at, okay, I'm centering things at the origin just for simplicity, but you could do exactly the same thing at any fixed vector in the normed vector space x. if you had some vector A, you can look at A and perturb it a small amount in the direction of V, and the same definition applies. So this proposal gives you a function, well, it gives a candidate for the derivative at a point. That being the derivative at 0 is the function which takes a vector v to this limit, which is a vector over in y, where that exists. I mean, assuming that exists. So that's not quite good enough. So let's see, drawback. In the one-dimensional case, the derivative was a linear map. I mean, maybe that's just a quirk of one dimensions, but in a sense, what the derivative does is it gives you a good infinitesimal approximation to the behavior of the function at the point that you're interested in. Now, an approximation, well, you know, if it's a really good approximation, that's good, so long as it's useful to work with. So the function itself is a very good approximation of itself, but it's complicated. So really what we want to do is get a good linear approximation, because linear things you're now supposed to believe are easy, or at least linear maps are a lot easier to study than arbitrary differentiable maps. So the definition just of taking all the different directional derivatives has the drawback that it mightn't give you something that's linear. So proposal 1 need not result in f prime of 0, so it's a map from x to y, but it need not be linear. Let's see. Yeah, let's take an example. So if I have f, a function on R2, and let's say it's just equal to x1 times x2 times x1 plus x2, all divided by the norm squared in the Euclidean sense of x. That's provided x1 and x2 aren't 0, and then let's just set it to be 0 if x1 and x2, I mean, if we're at the origin. Okay, so we can compute, so if v is v1, v2, let's see what happens when we take the directional derivatives. So the directional derivative in the direction v of f at 0, it's kind of cumbersome to say, is just f at t times v minus f at 0, which is 0, over t. So let's just substitute in for that, and you get a factor of t for x1, x2, and x1 plus x2. So this is t cubed, v1, v2, v1 plus v2, divided by, well, t squared, just coming from the f of t applied to v, and then I divide by t again, so that's t cubed, and then the t cubes cancel, so this is just okay, so the directional derivative of f at the origin in the direction v is just f at v. So this is a case, this is sort of motivating why I was saying the directional derivatives, or the collections of directional derivatives, give you a really good approximation of f at 0, but it's no simpler than f at 0. And then what's happening here, of course, is that this numerator is homogeneous of degree 3, and the denominator is homogeneous of degree 2, and any time you have a ratio of things differing by 1 in homogeneity, dividing by t will give you back the thing that you started with. Okay, so this is saying that you can have all the directional derivatives and not get a linear map. So if you like proposal 2, well, let's just insist that you get a linear map. Say f is differentiable at 0 if the directional derivatives define a linear map. From x to y. So that seems better. That's saying, well, we kind of know what the infinitesimal approximation of the function should be. It should be the directional derivative, at least following sort of the intuition of the one variable case. And we want a linear map, so we just demand that we get a linear map. It turns out, well, now this thing has a name. It gets called, not Fréchet's, Gatto's derivative. So this is not the definition of the derivative that we will use. And the reason we won't use it is because of things like the example I'll do in a second. But it's not a completely disastrous definition. There are situations in which the definition that I'll get to in a second, which is sort of a more robust one, just doesn't hold for functions that you still care about enough to want to have some notion of a derivative. And then if you can't have what you really want, you can sort of make do with what you've got. So this is not completely useless, but it's not good enough for the purposes of this course. So the example that I want to consider now is just let omega be the following region in the plane. So let's see if that's a, so you're supposed to believe that this is y equals x cubed, and then I want to have here, that's supposed to be 1, y equals x squared. Okay, so, and then the region that I care about is just the stuff in between. Okay, and then, so it's just this kind of little slice that's bounded between the graph of y is x cubed and y is x squared between 0 and 1. Okay, so this is also 1 up here. Okay, and then the function I want to consider is just the indicator function of this set. So this is just equal to 1 if your vector is, your point, sorry, is in omega, and 0 if x is not in omega. Okay, so now let's see what happens. Sorry, I should say it's the open region. So omega is the points x1, x2, where, let me see, I guess v1, sorry, x1, 0 is less than x1 cubed, is less than x2, is less than x1 squared. Okay, so I have strict inequalities here, so the origin is not in omega. And then the point is that you can check that for all v in R2, the directional derivative of this function f at 0 in the direction v is 0. And why is that? Well, it's just that the tangent lines of both y equals x squared and y equals x cubed at the origin are flat. So if you take x2 equals 0, all those points lie outside omega, so you get the directional derivative vanishes. If you take any, so this is where the picture isn't very good. If you take any line with positive slope, then if you just calculate, you see that, okay, there will be a portion of the line which lies inside omega, but because these tangents are horizontal at the origin, and this has positive slope, for very, very small multiples of your vector v, it will lie, if you like, above both the graph of x squared and x cubed. Okay, so all the directional derivatives of this function exist at the origin. They all vanish, so they define a linear map, which is the zero linear map. But, well, now it's a matter of taste, really. This function is not even continuous at the origin, right? So, but f of, say, t cubed plus t squared over 2, right, just the average of these guys, is equal to 1 for all t in between 0 and 1, let's say. And the limit of this is the origin as t goes to 0. So my function, which is possesses all its directional derivatives at the origin, and those directional derivatives define a linear map, fails fairly spectacularly to be continuous at the origin. So if you wanted to think of the derivative as being like sort of better, an improvement on continuity, then this definition isn't good enough. So you can have all the directional derivatives existing, you can have them patching together to give you a linear map, and your function's still behaving relatively unpleasantly. So the definition that we actually want finds a way of sort of excluding this. And if you think about what's happening here, somehow in every direction, you eventually end up being in a sort of domain where f vanishes, but which direction you're in, how small you have to get before that happens, depends a lot on the choice of direction. So the way to sort of get out of this issue is to demand, if you like, that the directional derivatives sort of all approximate the function at the same kind of uniform rate. Okay, so the definition that is, if you like, proposal 3, the one that works, is the following. If f is a function, so I'll kind of try and keep this notation standard. So you open in x and y normed vector spaces. And A is a point in U. We say f is differentiable at A if there's a linear map let's call it alpha, from x to y, strictly speaking, if we were working in infinite dimensions, I would say here continuous linear map, but I only care about finite dimensions in this course, and then all linear maps are automatically continuous. So I have a linear map alpha from x to y such that if epsilon, which is going to be a function from u to y, is defined by epsilon vanishes at a, and f of a plus h, so if I perturb f moving in the direction h, is f of a plus my linear map applied to h plus the norm of h times epsilon of a plus h. Okay, so all of this expression is just saying take f of a plus h, subtract f of a, subtract off the linear approximation that's supposed to be our derivative. That gives you some vector. That vector should go to 0. So that's, and then I need to finish off my sentence. And epsilon of a plus h tends to epsilon of a, which is 0 as h goes to 0. Okay, so this is saying that there is a linear map with the property that, if you like, the error between the function, the actual value of the function f of a plus h, and the approximation given by f of a plus this linear map applied to h, the difference between the two, so the error, you can write as the length of h times something, and that then when you divide everything by the length of h, this still goes to 0. So it's saying that the linear map alpha applied to h gives you an approximation to the function f of a plus h, which is at least as good as the length of h. It's well, actually, because we know all linear maps are bounded, you can see from that fact that there can be at most one linear map with this property. Okay, so let's just rewrite that just to make it clear. So thus, that is epsilon of a plus h is equal to f of a plus h minus f of a minus alpha of h, all divided by the norm of h, and then we're just saying that that error is going to 0 faster than the norm of h. Okay. If this condition holds, then if this holds, alpha is the derivative of f at a, and then, well, if you look at textbooks, you will see a whole variety of different notations, and is denoted possibly lowercase df at a, possibly uppercase df at a, and possibly both upper or lowercase with the a as a subscript. I think I will tend to use this or this. The reason for not writing this is because this thing is a linear map. So you'll want to write the linear map applied to a vector becomes df of a of v, which just gets kind of clunky. And so the usual convention is to write, say, something like df of a acting on v, like that. But so this is what's called this definition is, if you want a name for it, the Fréchet derivative. And it's also often referred to as the total derivative. Which is not a great name, but it comes from, as we'll discuss probably next time, the notion of partial derivatives, where you sort of fix some directions and see what the variation of the function is in some subset of those directions. And those being partial derivatives, then what's the thing that isn't partial? Well, it's total, I guess. So total derivative is a fairly common term, though it's not really a particularly good one. Fréchet derivatives is sort of the formal term. It's this, yes, sorry, what to say? What this definition is doing compared to the definition where we just ask for the directional derivatives to exist and form a linear map, is that it's asking for this error to go to 0 when you divide by norm h, so it's uniform in like the sphere of vectors of any given length. So it's uniform in a sense in the directions. So the difference between the Fréchet derivative and the Gatto derivative is that the Fréchet if you like, derivative demands the directional derivatives to converge sort of uniformly in the direction. On the sphere in X, so that's the so really that's just taking the unit sphere as sort of the vectors of length 1 as representatives for the space of possible directions you can perturb in. Okay. And just to point out, if f is Fréchet differentiable, at A, then all the directional derivatives exist. And in fact, the directional derivatives of f at A are just the Fréchet derivative applied to the vector. And let's just check that to see that we understand what the definition is actually saying. So indeed, what's the definition of this guy? We want the limit as t goes to 0 of f of a plus tv minus f of a minus, if you like, t times this, all of this over t equals 0. But if you just look at what the Fréchet derivative definition gives you, the limit as t goes to 0 of f of a plus t times v minus f of a minus the Fréchet derivative at A applied to t times v, all divided by the norm of t times v, equals 0. So this is just the difference that is epsilon of A plus t times v. And then if you just work out what this is the limit as t goes to 0 of, I guess, t divided by the absolute value of t times norm v times f of A plus tv minus f of A minus t, taking the scalar out of the linear map, df of A at v. So this is bounded. So because this goes to 0, this goes to 0, and that means that this vector here satisfies the definition of the directional derivative. Okay, so the Fréchet derivative is the linear map you get by patching together the directional derivatives. So if you like, if you have a function whose directional derivatives exist, the question of whether it's Fréchet differentiable or not is a property of the linear map you get by piecing together the directional derivatives. It's saying that linear map has to be a good approximation to the function in the sense that it approximates the function sort of at least as well as the norm of the difference between A and A plus H. Okay, so next time we'll study sort of the basic properties of the derivative and see that things like the chain rule have an analog for the Fréchet derivative.